So images are used in medicine to diagnose anything from a broken bone to heart disease to stroke and, of course, all different types of cancers. And one of the powers of imaging is that it can allow us to detect the disease before any of the symptoms are obvious. So we can then treat it early, which is much more likely to be a successful treatment. And another power of imaging is that it allows doctors to determine which specific treatment is appropriate for a specific patient. So not all broken bones, for example, are the same, so we wouldn't treat them the same way. Now, let's see what happens in the diagnosis of mental illness. This looks very different. The diagnosis is done based on the patient's description of his or her own symptoms. And because of that, it's typically done very late, because the symptoms have to become very severe for the person to seek help. And then the treatment happens typically by trial and error. So often a person has to go through multiple combinations of drugs and therapy to find one that works. And so if we could harness modern neuroimaging to be able, first of all, to catch psychiatric disorders earlier, and also to be able to determine precisely which treatment is appropriate for which patient, we could make a big impact on these patients' lives. And these patients are often us in one or another point in our lives. So at the same time as we're trying to introduce neuroimaging in psychiatry, there is a rethinking going on within the field of psychiatry about how diagnosis is done. And conventionally, there are these discrete categories, these boxes, like depression, anxiety, bipolar disorder, etc. And based on the patient's symptoms, the patient is placed in one of these boxes. And there are several issues with this. First of all, very different cases end up within the same box. Then it's unlikely that a person will fit neatly into just a single box, because many of those disorders often happen at the same time. And then which box you fall in cannot predict precisely which treatment will work for you. So the thinking right now is that maybe psychiatry should move from the categorical view to a dimensional view, where there are multiple continuous axes that correspond to our reward response or fear, anxiety, etc. And now a person is characterized by a point in this multidimensional continuous space. And the idea is that this point will be much more informative for tailoring treatments to target an individual rather than a whole box. The question is, how do we place a person in these axes? So for the boxes, we have some questionnaires, and based on the score on these questionnaires, we would place someone in one of the boxes. And the hope is that with the rich set of features on the function and structure of the brain that we get from neuroimaging, we can place someone on these axes. And I'm going to talk about one particular type of feature, which has to do with these fiber bundles that connect different parts of the brain and make up the whole interior of the brain, which is called the white matter. And specifically for psychiatric disorders, we care about some specific connections that go between regions that are responsible for the things that I talked about in the previous slide, like reward, fear, anxiety, etc. So there are hypotheses that neuroscientists have about which specific circuits, sets of these regions, are responsible for which function, and which of them are affected for each type of psychiatric disorder. So the hypotheses have to do with which of these connections are hyper versus hypoconnected. So typically we expect that the connections that facilitate our emotional response to stimuli would be overemphasized in mental illness, whereas the connections that facilitate our exerting executive control on those responses would be impaired. And for a very long time, the only way that neuroscientists had to map these connections was by taking apart a dead brain like this. But these days, with the advent of something that's called diffusion-weighted MRI, we are able to map these bundles in a living human being. And thanks to the Human Connection Project, which introduced some major advances in the acquisition technology for these types of scans, we can now, within just 10 minutes, acquire a very high resolution and high SNR scan of the whole brain that can allow us to get this kind of image. And so now that we know how to acquire this data, the question is, how do we analyze it, and specifically, how do we use it to study these disorders of brain circuits? And where does this data come from? It comes from the water molecules that are all over our brain. And they're never static, they're always moving around randomly, and this is called diffusion. In the absence of any barriers, this diffusion would be isotropic. So a water molecule would be equally able to move in any particular direction. But inside these fiber bundles, because the water molecules cannot permeate the walls of the fibers, it's much easier for them to move parallel to the bundles than perpendicular. And so by figuring out in which direction most of the diffusion of the water molecules is happening, we can infer how the underlying fiber bundle is oriented. And we get this information from some images that are called diffusion-weighted MRIs and give us information about how much diffusion there is in each particular direction at every location in the brain. Then we combine this information from all these different directions to determine which is the preferential direction of water molecule diffusion at every point in the brain. And this is what those red lines that you're seeing there are. Then something that's called a tractography algorithm will follow these diffusion vectors around the brain to reconstruct these images of the white matter fiber bundles. And typically we initialize this algorithm at every single location in the brain multiple times, and we end up for one of these high resolution images that we can collect thanks to the Human Connectome Project methods. We end up with massive data sets that contain maybe millions of these curves. And so then the question is, how do we parse these millions of curves to identify specific connections in the circuits that we're interested in? And our group has developed a couple of different approaches, both a supervised approach and a unsupervised approach. And unfortunately, the videos don't look like they're working. Sorry about that. And the common theme of these approaches and the novelty of these approaches is that they take advantage of the local anatomical neighborhood information of these bundles. So as a function of where you are along the path, who are you likely to meet to your left, to your right, anterior, posterior, in terms of other anatomical structures in the brain. And because it takes advantage of this information, it allows us to compare different individuals without having to perfectly align them to each other, which is a very difficult problem. So the supervised approach learns this structure, this neighborhood structure, from a set of training data, whereas the unsupervised approach, which was developed by Viviana Silas, who's somewhere in the audience, and you can ask her more about it, uses the similarity of these neighborhood information from different curves to group them into bundles. And all of our tools are open source and available publicly through the FreeSurfer software package that's used by labs around the world. And I'm going to show you an example of applying the unsupervised approach to the data that we're collecting as part of the BANDA project, that stands for Boston Adolescent Neuroimaging of Depression and Anxiety, where in collaboration with MIT, McLean Hospital, and Boston University, we're collecting scans from adolescents with the full range of depressed and anxious symptoms, rather than getting subjects that fit neatly into little boxes. And what I'm showing here is some of the clusters that predict anhedonia, or the inability to feel pleasure, for all subjects, regardless of whether they were classified as depressed, anxious, both, or neither, healthy. And so this is just an example of how these neuroimaging-based features allow us access to these continuous axes that we're looking for. And at the end of this project, this data will be publicly available for others to test their methods on and to accelerate discovery through the Human Connectome Project database. And I'm going to end with talking a little bit about what is the major obstacle to progress in our field and how our group is working to get around that. The problem is that we don't have ground truth. So we know the main highways of the brain, and we can train an algorithm easily to find those, but beyond those main highways, we don't know the full circuitry diagram of the brain. And because of that, we cannot take advantage of all the recent developments in learning. And the problem is that we cannot get that information from the usual scans that we can collect in the clinic, because the voxels are too big and they contain multiple bundles of axons. And as soon as you have two bundles in a voxel, there are multiple very different configurations of the two bundles that give rise to the same diffusion measurement. And so a tractography algorithm that reaches that intersection will not know which way to turn, so it'll just get stuck. And the way we're getting around this is by making our voxels so small. And again, sorry, oh, this is working, perfect. That's the best one. And making our voxels so small that each contains only a single fiber bundle. And so getting rid of some of those ambiguities. In order to do that, we have to do a very long scan. That's not possible in live subjects. And so we do them in dead brains. And we're picking out of human brains these areas that contain a lot of those ambiguities. And then we cut out those blocks and scan them one by one over an entire weekend in a very strong scanner that is usually used to scan mice. And then we can collect this microscopic quality data. And then we can put them all together digitally back into the whole brain context to develop these highly accurate models of brain circuitry. And our goal is to then use these as the ground truth to train algorithms to reconstruct those circuits accurately in the much lower quality, lower SNR, and lower resolution scans that we can collect in the clinic, so that we can use this to reconstruct accurate models of brain circuitry in patients and study them. And I'm going to end with thanking the group members that contributed to this work, as well as my collaborators in the BANDA project and in the Martino Center for Biomedical Imaging, as well as the funding agencies that contributed to this work. Thank you.